We're talking about 5.3 today, which is the double angle formulas. I'm going to go ahead and derive or prove this first one of what the sine of 2a is. And then you guys can hopefully be able to on your own, maybe look at the rest of them, or just to really kind of understand, hey, this is where they come from. So I can rewrite the sine of 2a as the sine of a plus a. A plus a is 2a. Now we can use the sum sine identity, because I know that the sine of a plus a, using my sum identity, is the sine of the first a, cosine of the second a, plus cosine of the first a, sine of the second a. Now you'll notice that cosine a, sine a, I can flip-flop that. I can write sine a, cosine a instead. So this is equal to sine a, cosine a, plus, flip-flop these around, I get the sine of a, cosine of a, which is equal to 2 sine a, cosine a. And that is my double angle identity for sine. So there it is. Sine of 2a is 2 sine a, cosine a. Now you'll notice that there are 3 cosine double angle identities. Now, one of them is never better than the other 2. However, we can utilize one of them over the other 2 based on the situation I have, and we'll see a little bit of that today. And lastly, we have the tangent of 2a. So you're going to want to know these. Again, if you really are in a pinch, you can derive them like I just did. However, they may be given to you on the testing quizzes. So let's use some of this. If the sine of a is negative 4/5 in quadrant 3, let's find out what the sine of 2a is. First order of business, we got to draw a picture. I'm in quadrant 3. Here's my a, negative 4, 5. Hopefully you can recognize this x-axis as negative 3. Now I'm going to rewrite the sine of 2a using my sine double angle. 2 sine a, cosine a. Well, 2 times, I'm given what the sine of a is, negative 4/5. Or we can see on our triangle, hey, opposite over adjacent, opposite over hypotenuse. Times the cosine of a. Well, the cosine is negative 3 divided by my hypotenuse, so negative 3 over 5. Multiply across, 2 over 1 here. 2 times negative 4 times negative 3. Well, that gives me a positive 24 over my denominator, 25. We also have the cosine of 2a. Now, we can utilize the exact same picture, or knowing that one of my cosine double angle identities is 1 minus 2 times sine squared of a. Well, notice that I'm already given the sine of a. So let's utilize a cosine double angle that only has to deal with sine of a. That way I don't even have to draw a picture. I can just substitute negative 4/5 in. So this is equal to 1 minus 2. Well, this is the same as sine of a squared. So I can just substitute negative 4/5 in for sine and then square it. Simplifying that out, that's 1 minus 2 times 16 over 25. One minus 32 over 25 if I multiply that by 2. So this is equal to 25 over 25. That's my 1 minus 32 over 25. Remember, when we subtract fractions, we have common denominators. The denominator stays the same. And I subtract the numerators. So negative 7 over 25. Remember, I didn't use a picture because I can just utilize a cosine double angle theorem that only utilizes a sine of a, which I have. Alright, notice I'm dealing with cotangent of 2a here. Now, I could have dealt you tangent of 2a, but I wanted to do cotangent of 2a to kind of hammer in a point here. Now notice this is the same as 1 divided by the tangent of 2a. And if we think back to our tangent double angle, the tangent of 2a is equal to 2 tangent of a divided by 1 minus tangent squared of a. Since I'm dealing with cotangent, which is 1 over the tangent of 2a, I can utilize this formula here and just reciprocate it, or flip the fraction to make it a cotangent double angle theorem. So to figure out what the double angle of the identity of cotangent of 2a is, I just take this fraction here and I flip it. So this is 1 minus the tangent squared of a divided by 2 tangent of a. And all of a sudden I have my double angle cotangent identity. Now we're going to use the same picture. This is a, -4, -3, and 5. So substituting in tangent of a now, my identity becomes 1 minus, well, the tangent of a squared. Tangent of a is -4 over -3, so we get a positive 4 over 3 squared. My negatives cancel there. Divided by 2 times the tangent of a. Tangent of a is 4 over 3 again. Well, let's square some stuff out. Get things as simple as I can before having to deal with this complex fraction. So on top I have 1 minus 16 over 9 times 8 over 3. Now I could do this whole common denominator on top, figure out one fraction and flip, or there's a trick that we can use by figuring out, hey, well, this is 1 over 1, right? Let's figure out the common, the greatest common multiple, or the multiple that has to deal with 1, 9, and 3, my denominators. Well, notice that all of them go into 9. So what I'm going to do is I'm going to multiply each of them by 9. Because all three of them, 1, 9, and 3, go into 9. And let's see what happens. So 9 times 1, I get 9, minus, well, my 9's cancel, so I get 16, divided by, well, 3 goes into 9 3 times, so 24. So I have 9 minus 16, or -7 over 24. So -7 24ths is my answer. So what if the cosine of x is 1 over root 5 with x in quadrant 4? Again, I'm going to rewrite, well, let's rewrite this cosine 2x now. Now remember, I can choose from 3 of them, and I'm given cosine of x. So let's try to utilize a cosine double angle identity that only has to deal with cosine x. That way I don't even need a picture. Well, it just so happens that the cosine of 2x is 2 cosine squared of x minus 1. Remember, x, theta, a, they're interchangeable, so it doesn't really matter what this letter in here is. Well, I know what cosine x is, so let's just plug in everything I know. Kind of a bad equal sign there. So I have 2 times cosine of x squared, that's the same thing. So we have 1 over root 5 squared minus 1. Or when we simplify this out, this becomes 1 over 5. So 2 over 5 minus 1. Well, 1 is just 5 over 5. So I get 2 over 5 minus 5 over 5. Or -3 over 5. So what if we had the same setup here, but sine of 2x? Well, the only identity I have for sine 2x is 2 sine x cosine x. Now I know cosine x, but I need to find out what sine x is, so we'll need a picture. So I'm in quadrant 4 here. This is my angle x. And I know my cosine, or adjacent over hypotenuse, is 1 over root 5. Well, we can use Pythagorean theorem, and we get that this is negative 2. If you can't really see that off the top of your head, this is 1 squared plus, well, this, we'll call it a squared equals root 5 squared. So we get 1 plus a squared equals 5. A squared is 4, so a is 2. A is 2. We're in the negative direction. Okie dokie. So this becomes 2 times the sine of x is negative 2 over 1. Oh, sorry, negative 2 over root 5 times the cosine of x. Well, that's just 1 over root 5. We're given that. So multiply across 2, negative 2. We get negative 4 on top and 5 on bottom. So I get negative 4/5. Alright. Tangent theta is equal to 4/3, and theta is in quadrant 3. Find cosine of 2 theta. Now, let's use the only cosine double angle that we haven't used, which is cosine squared of theta minus the sine squared of theta. Now, I have tangents, so I'm going to need to draw a picture. I'm in quadrant 3. Here's my theta. And I know that tangent here is opposite over adjacent, so 4 over 3. Notice I'm negative in both directions, though. It's important to remember I'm in negative, so my hypotenuse is 5. Now I can figure out what cosine theta and sine theta are. Cosine theta is adjacent over hypotenuse, so this is negative 3 over 5 squared, minus sine squared theta, negative 4 over 5 squared. So I get 9 over 25. I'm squaring a negative, so it's positive. Minus 16 over 25. Or when I simplify, negative 7 over 25. So the cosine of 2 theta is negative 7 over 25. Now, the secant of 2 theta. Remember, the secant of 2 theta is just 1 divided by the cosine of 2 theta. Well, how about that? I already found out what the cosine of 2 theta is. It's negative 7 over 25. So if I have the cosine of 2 theta, don't do more work than you need to. Just plug it in as the reciprocal of what cosine is. If I know the cosine is negative 7 over 25, the secant of 2 theta would be negative 25 over 7. They're just reciprocals of each other. So if I found out what cosine 2 theta is, flip that fraction and I get secant of 2 theta. Easy as that. Alright, so let's use exact values to show that one of these identities work. One of the cosine double angle theorems. Well, what's the cosine of 60? That's just 1/2. If you need some special triangles, it's okay. Equals 1 minus 2. What's the sine of 30? Just 1/2 squared, because it's sine squared of 30. So let's see what I have on the right here. 1 minus 2 times 1/4. This just becomes 1 minus 1/2, or 1/2. Well, how about that? Works out. Let's try another one. The sine of 90 equals 2 cosine 45, sine 45 cosine 45. Well, the sine of 90 is just 1, straight up in the unit circle. Equals 2 times sine of 45 is root 2 over 2 times cosine 45, same thing, root 2 over 2. So when I multiply across, 2 times root 2 times root 2, root 2 times root 2 is 2. Times another 2 gives me 4. Divided by 1 times 2 is 4, or just 1. Again, works out just fine. So there are a couple examples, like concrete examples, of these double angle theorems working out using exact values. So let's do some simplifying now. Now I have a cosine squared minus sine squared. Now hopefully you recognize this as a cosine double angle. I'll rewrite it for you. The cosine of 2a, one of them happens to be cosine squared of a minus sine squared of A. So we're going to let 15 degrees be my A. Using this identity here, this becomes the cosine of 2A. Well, 2 times 15 becomes 30 degrees, which we know as root 3 over 2. Tangent of 3 pi over 8 over 1 minus tangent squared of 3 pi over 8. That just looks like a mess. But let's do the same thing. I happen to know that the tangent of 2A is equal to, well, tangent of A all divided by 1 minus tangent squared of A. So we're going to let my 3 pi over 8 be my A value. I missed a little bit there. There we go. So using this identity here, this is going to be equal to the tangent of 2 times my A value, or 2 times 3 pi over 8. Well, this becomes a 4 on the bottom, so the tangent of 3 pi over 4. Well, what's happening at 3 pi over 4? That's going to be in my second quadrant, where this is 3 pi over 4. So my reference angle here is pi over 4. So if we want to make a triangle here, we label my side lengths as a negative 1, 1, root 2. So the tangent of that is going to be 1 divided by negative 1. Or negative 1. Simple as that. Just recognizing my double angle identity, and then all of a sudden, boom, we got our answer. Alright, we're going to do the hard one here last. Move everything up because we're going to need room. Hey, so we are proving an identity here. So I cannot touch this right-hand side. Gotta leave it alone. But I can rewrite this cosine of 3 theta. Now I don't know a triple angle identity, but I do happen to know that cosine of 3 theta is equal to the cosine of 2 theta plus theta. So I can turn it into a angle sum identity. Using my cosine sum identity, I know that's equal to cosine of my first angle, so 2 theta, times the cosine of my second one, so theta, minus sine squared, not sine squared, apologies, sine of 2 theta, sine again, my apologies, sine of theta. Now, I have these double angle identities, cosine 2 theta, sine 2 theta. Now you're going to have to kind of recognize what I want in the very end. I want only cosines right now. But I'm going to start by writing this cosine of 2 theta. Now I have 3 to choose from. I'm going to choose to write it as the cosine squared of theta minus sine squared of theta. And that's multiplied by cosine theta from what I had before. Minus, well, I only have one sine of 2 theta identity. That's 2 sine theta cosine theta. And that's multiplied by sine theta still. So let's multiply everything out. Let's expand stuff. Distributing my cosine theta, I get cosine cubed of theta minus sine squared theta cosine theta. So that's just multiplying out and distributing that cosine theta. Minus, distribute this out, 2 sine squared of theta cosine theta. Just distributing that sine theta in. Now I have a minus 1 sine squared theta cosine theta minus 2 sine squared theta cosine theta. So I have minus 3 of them. So this becomes cosine cubed of theta minus 3 sine squared theta cosine theta. That's just combining my like terms. Now right now I have the sine squared theta in there. At the very end of the day, I want only cosines. So I'm going to rewrite sine squared theta as a 1 minus cosine squared to get rid of sine. So this cosine cubed theta stays the same. Minus 3 times 1 minus cosine squared theta cosine theta. Now again, distribute everything out. I have a 3 times a 1 times a cosine theta. This becomes minus 3 cosine theta. Now I have a minus 3 times a minus cosine theta. So these minus signs cancel. It becomes a plus 3 cosine cubed theta. Now notice I have a 1 cosine cubed and a 3 cosine cubed. So I have 4 cosine cubed theta minus 3 cosine theta, which if you look up top is exactly what I want. So go ahead and write your summary and any questions you have, and please take a look at this homework assignment. Again, that very last problem, you might want to look at that again. Hint, hint, it might be on a quiz or a test coming up, and you're going to want to know how to prove something of that caliber.